afternoon. I'm Vladimír Kučera, and I'm going to report on the research results of the Department of Platforms, abbreviated PLAT. In fact, I am the only member remaining to report the results of this department. The other members have already reported elsewhere. So my results for the last year are here. One article in the IEEE Transactions on Automatic Control, which is a D1 journal, and one keynote lecture at the International Conference on Informatics in Control, Automation and Robotics, held in Porto, and the related paper in the proceedings. I have chosen to tell you more details about the first result, which is a basic research result. Or maybe I should use this. Is it okay?
No, you should use it for recording.
Okay. Yeah, okay. So, which is a result of basic research in systems and control theory, and the question is, can the system's zeros be altered by feedback? First, of course, we have to define the systems to be discussed. We consider linear multi-input systems of this form, state space equation, where x is the state, u is the input vector, y is the output vector, a, b, c, d are real matrices. Then, the system's eigenvalues, including their multiplicities, is specified by the elementary divisors of the matrix A minus Si. This is well-known result. The finite zeros of the system are specified by the finite elementary divisors of this matrix, sigma. And the system's zero at infinity, for s equal to infinity, including its multiplicities, it's specified by the infinite elementary divisors of this matrix. So this means that the eigenvalues, zeros, finite or infinite, are in fact part of the Kronecker invariants of this matrix sigma. Now, to modify systems properties, we use feedback. And the most powerful feedback is state feedback, which includes the entire state x. The form of the feedback is u is fx plus gv, where v is a new reference input. And now it's important to distinguish regular and non-regular feedback. If the matrix G is square and non-singular, the feedback is said to be regular. Otherwise, it is non-regular. So non-regular means typically G is either tall or fat matrix, but not square. Then the resulting closed-loop system is given by these equations, and usually in control applications it is required to be stable, meaning that all eigenvalues of the A plus BF matrix having negative real parts. Now, the first claim is that regular state feedback can alter poles, but not zeros. Assuming the system is controllable, its eigenvalues can be modified at will using regular state feedback. In particular, the system can be stabilized, for example. But the zeros, however, cannot be altered. They are invariant with respect to the regular state feedback. So if you see, this is the state, this is the sigma matrix for the closed loop system, and this is the one for the original system, and they are related by a non-singular transformation, provided G is non-singular. So they have the same invariance. So zeros cannot be changed at all by feedback which is regular. Especially difficult are zeros and they are critical to achieving the desired performance. Even in stable systems, unstable zeros, called non-minimum phase zeros, may result in an initial undershoot. You see the red one curve. This is a very undesirable behavior. For example, just imagine a fictitious airline company called the non-minimum phase airlines, whose flights always start first in the wrong direction. And the result of the paper is that zeros can be modified, but only by non-regular state feedback, which is more powerful. And the paper presents the necessary and sufficient condition for a pre-specified set of zeros to be assignable by state feedback. And the result is that new zeros of any value, finite or infinite, can be added. But the existing zeros remain always in place. Only their multiplicities can be increased. And the increase always comes from the unobservable part of the system, which is a part of the system dynamics, which can be controlled, but it cannot be observed. And the role of the non-regular state feedback is to connect it to the system in such a way as to achieve the goal. But caution, non-regular state feedback can destroy the system's stability, even stabilizability, while modifying the zeros. It can destroy almost everything. So we must stabilize the system first, and then authorize only stability-preserving state feedback to ensure stability. And the question arises, it is useful at all to add zeros? Oh yes, it is. For example, in system decoupling. The task of decoupling is to eliminate the couplings which exist within the system using state feedback, so that each output is influenced by only one input. So here, okay, the coupling is 2, and this one is to be eliminated. So how to do it? Simply, the idea is to subtract -2 here, but first we must create a box like this here, and this is the zero to be added. Here is how we create a copy of the coupling and how it can be subtracted from the original. So in black, it's the original system. It has one integrator here, which is not observable, but controllable. So we use it to create a box like that, having 0 at +1. This is done by the red couplings here. And when we had such a block, which is exactly the same as here, we connect it to the input U1. So now we have a copy of this coupling here. And we subtract it. That's it. So we created an additional 0, which is a copy of the existing ones, with the aim of eliminating an unwanted coupling. Decoupling is useful. It has been successfully applied, among others, to eliminate the couplings, for example, between the active front and the rear wheels of a 4-wheel steering vehicle to achieve yaw stability, overturning, or to design active vibration isolation tables and suppress internal interactions in a precise platform positioning, or to control the top pressure in a blast furnace for in the presence of strong couplings between the top pressure and the top gas cleaning and recovery system of the furnace. There are other applications in the literature. So, thank you for your attention. That's all.
My name is Jochman, and I'm presenting results of RICAIP Testbed Prague. So first of all, I would like to mention 7 conference papers. One of them A star, 2 of them A, and 3 will be ranked this year. Between other results, I can mention a functional sample, 2 verified technologies, and software. One of those software we are getting ready for licensing this year. We also contributed 2 or 3 chapters in Professor Mařík's book. Those were additive manufacturing and digital twin chapters. We also made some contribution on an industrial conference, Siemens Realized Life, between one of the largest companies in Europe. And also, I think that it is good to mention that thanks to the long-term cooperation with our partner Continental AG, they were capable to get Global Lighthouse Network Award, which is top 170 companies in the world which are using like the most high-tech technologies, artificial intelligence and so on. And for, starting for the next month, we are also getting cooperation with Meltier company, which is manufacturer of robotic like extruders from metal. So based on this cooperation, we will be capable to deploy these solutions to end customers and companies. And now I would like to give word to my colleague Zeman. And sorry, here are some illustrations of the results.
Okay, hello, my name is Zeman. Today I will be presenting one of our work on object pose estimation using implicit representation for transparent object. Why we do this is because as part of flexible production line, we want to introduce new objects into robotic manipulation pipeline as soon as possible. One crucial part of this manipulation pipeline is 6D pose estimation, that is where the object is located in space and how it is oriented, so it is able to be picked up by a robot. Furthermore, due to the costs and time savings, we also are looking into using only a single RGB camera, and we would like to have a generalized method which doesn't need to retraining on any specific object. Furthermore, in this work, we focused on transparent objects, which are one of the harder objects to manipulate due to their non-Lambertian behavior, due to the reflexiveness and transmission. This we tackled using implicit representation, more specifically neural radiance fields. The representation of a new object, due to these benchmarks with other methods, we did partially synthetically, where in simulation we applied different shaders, extracted the images, and used instant NGP for getting the representation of the object. This training takes around 2 minutes. Then we use this representation we basically adjusted Megapose render and compare pipeline, where we replaced the initial mesh rendering with this rendering from instant NGP, which we believe that the photorealistic behavior of instant NGP and neural fields increases the precision. Furthermore, we also fine-tuned this network to be able to work with these nerves. As I said, custom fine-tuned dataset it is also created synthetically. We then evaluated on 4 datasets, varied datasets, which included both classical objects and transparent objects as house cat under which are more only transparent object with very backgrounds, and then even some industrial metal objects. We used multiple metrics listed here for evaluation. Our results are highly positive. We observed that even without needing for retraining, in certain cases, just implementing the rendering increased the results of this method, while for the fine-tuning increased it only in case of transparent object, but that is to be expected. We lost some generality. Okay. This is basically visualization because the numbers are nice, but as you can see, this is projection of the estimation in the space of the different objects. In green, you can see the ground truth. In orange, this is just replacing the rendering, and the purple is for the fine-tuning. Just to be mention it once more, we only use a single 2D image at the input. So, in conclusion, another part, we don't only need to necessarily have the items scanned from simulation, so we can just retrieve this implicit representation from the image, which you can see in the from set of sparse images, which you can see downwards in the bottom. Furthermore, our method does not require any retraining for specific objects. The render and compare works without it. We validated also our results on multiple data sets. Our next part of research is actually deploying this pipeline into like real robotic manipulation. So that will be all for me. Thank you for your attention. If you have any questions.
Questions? If not, so thank you very much.